There's a hidden force controlling your daily routine that you've probably never thought about. It decides when you wake up, what clothes you wear, what food is available at your grocery store, and even your mood patterns throughout the year. This invisible controller is a 23-degree tilt that happened when Earth was basically destroyed and rebuilt 4.5 billion years ago. Recent 2025 observations reveal shifts in seasonal timing in key regions, indicating our tilt is interacting with a changing climate in ways that are reshaping the rhythm of our planet. But to understand how this ancient angle controls your modern life, we need to go back to the catastrophic moment that created it. The ancient cosmic collision that controls your morning routine. The moment you wake up tomorrow morning, you're experiencing the direct result of a planetary catastrophe that happened when Earth was a completely different world. Your alarm clock rings at a specific time because our planet got knocked sideways by another planet 4.5 billion years ago. That collision still controls whether you wake up in darkness during winter months or bright sunlight during summer, and the timing affects everything from your energy levels to your body's hormone production. Early Earth, a molten world bombarded by hundreds of bodies, was struck by a Mars-sized planet called Theia during the chaotic formation of our solar system. Most protoplanets would eventually get ejected from the solar system or destroyed in collisions, but this particular encounter would change everything. Theia was following an unstable orbit that put it on a direct collision course with early Earth. The impact happened with a violence that's almost impossible to comprehend. Theia slammed into Earth at roughly 25,000 miles per hour, releasing energy equivalent to billions of nuclear weapons detonating simultaneously. The collision was so massive that it completely vaporized Theia and destroyed large portions of Earth's crust. Molten rock and debris shot thousands of miles into space, creating a ring of superheated material orbiting our planet. Over millions of years, this debris would gradually coalesce to form our moon. But the collision did something else that would prove even more significant for life on Earth. The impact knocked our planet completely off its vertical axis, leaving it permanently tilted at about 23.4 degrees. This wasn't a gentle nudge. It was like taking a spinning top and hitting it with a sledgehammer. Earth has been wobbling at this angle ever since, spinning through space like a tilted gyroscope as it orbits the sun. This ancient tilt still decides how long your winter nights feel today. The 23-degree angle now determines the exact length of every single day you experience throughout the year. In major cities across the globe, daylight duration swings by up to 6 hours between winter and summer solstices. In New York City, December days last just 9 hours and 15 minutes, while June days stretch to over 15 hours. London sees even more dramatic variation, with winter days lasting barely 7 hours and 49 minutes compared to summer days that extend past 16 hours and 30 minutes. The 2025 climate monitoring data shows these daylight variations are becoming more pronounced in certain regions due to atmospheric changes that affect how sunlight penetrates to ground level. Cities at higher latitudes are recording daylight duration differences that exceed historical averages by 15 to 20 minutes per season, a shift that seems small but has measurable effects on human circadian rhythms. Your body's internal clock evolved over millions of years to expect these seasonal daylight changes, but modern life often disrupts this ancient programming. Seasonal affective disorder affects approximately 5% of adults in the United States, with symptoms directly tied to reduced daylight exposure during winter months. The condition becomes more severe at higher latitudes where daylight variation is most extreme. Recent medical studies from 2025 show that even people who don't develop full seasonal depression experience measurable changes in sleep quality, appetite, and cognitive function as daylight hours shift throughout the year. The circadian rhythm disruption extends beyond mood disorders. Your body produces melatonin based on light exposure patterns that change dramatically between seasons. During winter months when daylight hours are shortest, melatonin production can begin up to 2 hours earlier than during summer, making people feel tired much earlier in the evening. This ancient biological programming assumes that seasonal light changes will remain consistent and predictable. Without that cosmic collision 4.5 billion years ago, Earth would spin upright like a perfectly balanced top. Every day would last exactly 12 hours of daylight and 12 hours of darkness, year-round, everywhere on the planet. There would be no spring awakening, no summer heat waves, no autumn harvests, and no winter snow. The temperature at any given location would remain virtually constant throughout the year, creating a world of permanent climate zones with no seasonal variation whatsoever. Dr. Sarah Chen, a planetary scientist at the University of California, explains that this hypothetical untilted Earth would have completely different weather patterns. Without seasonal temperature changes driving atmospheric circulation, we wouldn't have the complex weather systems that distribute heat and moisture around the globe. The tropics would be even hotter, the poles would be frozen wastelands, and the temperate zones where most humans live simply wouldn't exist. The seasonal changes created by Earth's tilt don't just affect temperature and daylight, they drive virtually every weather phenomenon on our planet. The tilt creates the temperature differences between air masses that generate storms, the pressure systems that create wind patterns, and the seasonal heating that powers everything from monsoons to hurricanes. Even local weather events like thunderstorms depend on seasonal temperature contrasts that exist only because of our planet's tilted orientation. Climate data from 2025 reveals that this 4.5 billion-year-old cosmic accident is now interacting with human-caused climate change in unexpected ways. The seasonal temperature swings created by Earth's tilt are becoming more extreme as greenhouse gases trap additional heat in the atmosphere. Winter warming is happening faster than summer warming in many regions, creating seasonal temperature patterns that haven't existed since long before human civilization began. The same planetary collision that determines when your morning alarm goes off also controls every hurricane that forms in the Atlantic, every tornado that touches down in the Great Plains, and every monsoon that brings water to billions of people across Asia and Africa. That single moment of cosmic violence 4.5 billion years ago created the tilted world that makes all these weather patterns possible. But in 2025, something unprecedented began happening to these ancient seasonal rhythms that had remained stable for millions of years. Why 2025's weather broke all the rules. Meteorologists around the world spent 2025 scratching their heads as weather patterns defied every prediction model they relied on. Seasonal forecasting systems that had worked reliably for decades suddenly became useless, missing major weather events by weeks and completely failing to predict temperature swings that shattered records across multiple continents. The computer models that predict seasonal changes are built on historical data spanning centuries, but 2025 proved that the past no longer predicts the future when Earth's ancient tilt starts interacting with a rapidly changing climate system. Traditional seasonal forecasting depends on recognizing patterns in how Earth's 23-degree tilt creates predictable temperature cycles year after year. These models calculate how much solar energy different regions receive as our tilted planet orbits the sun, then factor in ocean temperatures, atmospheric pressure systems, and historical weather data to predict what each season should bring. But in 2025, these tried-and-true methods failed spectacularly as the fundamental assumptions about seasonal behavior broke down. The first 6 months of 2025 became the second warmest first half of any year in recorded history, with global temperatures averaging just 0.08 degrees Celsius below the record set in 2024. This extreme warmth occurred despite moderate La Niña conditions at the start of the year, which typically suppress global temperatures and should have created cooler conditions worldwide. El Niño neutral conditions notwithstanding, NOAA reported January 2025 as the warmest on record, while March, April, and May each became the second warmest months of their kind in the temperature record. Temperature swings in 2025 reached levels that caught climate scientists completely off guard. The Western Mediterranean saw its highest short-term temperature spike since the deadly 2003 heatwave, making the 2025 warming particularly alarming for public health officials trying to prepare for potential summer disasters. Spring arrived weeks early across vast sections of North America and Europe, while other regions experienced winter conditions that lasted well into what should have been the growing season. Cherry blossoms bloomed in Washington, D.C., nearly 3 weeks ahead of their historical average, while apple orchards in Michigan saw their flowering period begin in mid-March instead of the typical late April timing. These shifts weren't gradual changes happening over decades. They were dramatic departures from normal seasonal timing that occurred within a single year. The jet stream, a fast-flowing river of air that circles the globe and helps create our weather patterns, behaved in completely unprecedented ways throughout 2025. This high-altitude air current normally follows predictable seasonal patterns as Earth's tilt creates temperature differences between the equator and the poles. But altered temperature gradients caused the jet stream to meander wildly, creating weather conditions that meteorologists had never seen before. The unstable atmosphere caused by warming air masses triggered extreme weather events across the hemisphere, including heavy downpours and flash floods that struck regions completely unprepared for such intense precipitation. Earth's 23-degree tilt acts like an amplifier for climate changes, taking small shifts in global temperature and turning them into massive seasonal disruptions. The tilt concentrates solar energy at different latitudes throughout the year, but when background temperatures rise even slightly, this seasonal energy concentration creates much more dramatic temperature swings than the warming alone would suggest. A 2-degree increase in average global temperature doesn't mean every place gets 2 degrees warmer. It means some regions experience 10 or 15-degree temperature swings during their peak seasonal periods. The polar vortex, a massive area of cold air that normally stays locked over the North Pole during winter, experienced what scientists called a spectacular breakdown in 2025. This breakdown occurred far earlier than any previous year, since reliable measurements began in 1958, allowing Arctic air to spill southward while warm air pushed unusually far north. Arctic record lows in sea ice extent in June 2025 underscore the tilt-driven polar amplification that's reshaping weather patterns across the globe. Farmers across the globe struggle to adapt their planting and harvesting schedules to seasonal cues that no longer arrived on time. Corn farmers in the Midwest found themselves planting in soil conditions that were either too wet from unexpected late spring rains or too dry from early heat waves that evaporated soil moisture weeks before the normal growing season began. Wheat farmers in Australia watched their crops suffer as seasonal rainfall patterns shifted dramatically, arriving either too early and causing flooding or too late to support proper grain development. Wildlife populations faced similar disruption as the biological signals they evolved to follow over millions of years suddenly became unreliable. If climate change causes caterpillars to emerge earlier, some species of birds may not be able to adapt to this change quickly enough to time their breeding seasons correctly. Migration patterns that worked perfectly for countless generations began failing as animals arrived at their destinations to find food sources that had already peaked weeks earlier or hadn't yet become available. Indigenous communities reported increasingly erratic weather patterns that disrupted traditional hunting, fishing, and gathering practices across Canada and other regions. These communities depend on seasonal patterns that have remained consistent for thousands of years, but 2025 brought shorter, less predictable winters, earlier springs, and more frequent extreme weather events that affected food security and required completely modified harvest scheduling. Climate scientists now recognize that 2025 marked a fundamental turning point, where Earth's tilt began creating entirely new seasonal behaviors that have no historical precedent. The seasonal chaos of 2025 represents just the beginning of a new era where Earth's ancient 23-degree tilt drives weather systems that behave unlike anything humans have experienced before. But nowhere is this transformation more visible than in the planet's most extreme regions, where the effects of our tilted world create phenomena so bizarre they seem to defy the basic rules of day and night. The midnight sun phenomenon that's expanding beyond the Arctic. The most extreme example of this transformation occurs in regions where the sun refuses to set for months at a time. Imagine living in a place where midnight looks identical to noon, where your body completely loses track of time because darkness simply doesn't exist. This isn't science fiction. It's the daily reality for millions of people living within the Arctic Circle, where Earth's 23-degree tilt creates the midnight sun phenomenon. And 2025 data shows this bizarre occurrence is becoming more intense than ever before. When our planet tilted sideways 4.5 billion years ago, it created an invisible boundary at approximately 66.5 degrees north latitude called the Arctic Circle. During summer months, the tilt positions the Arctic region so that it faces toward the sun continuously as Earth rotates, preventing the sun from ever dipping below the horizon. The sun traces a circular path around the sky, staying visible even at local midnight when it appears lowest on the horizon. In Svalbard, Norway, the northernmost inhabited region of Europe, residents experience uninterrupted daylight from roughly April 20 to August 22 each year. That's more than 4 months without a single sunset. At the North Pole itself, this phenomenon extends for roughly 6 months, from late March through late September, creating half a year of continuous day followed by half a year of continuous night. The intensity and duration of midnight sun varies dramatically based on geographic location. In areas closer to the North Pole, the sun remains bright and high throughout the 24-hour cycle. Further south within the Arctic Circle, such as in northern Norway and Iceland, the midnight sun appears like a perpetual sunset that never quite disappears, casting everything in warm golden and orange hues that photographers describe as magical, but locals know can become psychologically exhausting. Climate monitoring data from 2025 reveals that rising temperatures are fundamentally altering the midnight sun experience across Arctic regions. Atmospheric changes caused by increased greenhouse gas concentrations are affecting how sunlight penetrates through the air, creating more intense heating effects during the continuous daylight periods. Weather stations throughout Greenland and northern Canada recorded surface temperatures during midnight sun periods that exceeded historical averages by 3 to 5 degrees Celsius, intensifying the already extreme conditions. The psychological effects on people living through months of endless daylight prove far more complex than most outsiders realize. Human circadian rhythms depend on regular cycles of light and darkness to regulate sleep patterns, hormone production, and basic biological functions. During midnight sun periods, many residents report difficulty sleeping, changes in appetite, and a general sense of temporal disorientation where days blend together without clear boundaries. Dr. Alina Marchetti, a sleep researcher studying Arctic communities, documented significant increases in insomnia and mood disorders during 2025's midnight sun season. Her research found that even residents who have lived their entire lives in these regions continue to struggle with the biological challenges of perpetual daylight. Sarah Lindqvist, a nurse from Tromsø, Norway, describes the experience. By July, I'm taking melatonin supplements and using blackout curtains, but my body still thinks it's supposed to be awake at 2 a.m. You lose all sense of normal time. I've lived here for 30 years, and it never gets easier. Wildlife in these regions has evolved remarkable strategies to survive and thrive during months of continuous sunlight. Arctic terns time their breeding cycles to coincide with the midnight sun, allowing them to hunt for fish around the clock to feed their chicks. Caribou alter their grazing patterns, feeding more frequently during the cooler midnight hours when the sun hangs lowest in the sky. Polar bears actually become less active during the brightest periods, seeking shade and cooler areas to avoid overheating in the constant light. Plant life shows equally fascinating adaptations to perpetual daylight. Arctic flowers like the purple saxifrage and Arctic poppy photosynthesize continuously during the midnight sun period, growing and blooming at accelerated rates to take maximum advantage of the extended light exposure. These plants pack an entire growing season into just a few months of intense activity before returning to dormancy during the dark winter months. Local communities have developed cultural traditions around the midnight sun that help residents cope with its psychological challenges. In Greenland, people organize midnight baseball games, outdoor festivals, and group activities that take advantage of the endless daylight while providing social structure to days that otherwise lack natural time markers. These community events help maintain normal social rhythms even when natural light cycles completely disappear. The 2025 climate data reveals concerning changes in regions south of the Arctic Circle, where white night phenomena, periods of extended twilight that never reach full darkness, are becoming more intense and lasting longer. Areas in northern Scotland, southern Alaska, and northern Scandinavia that historically experienced only brief periods of extended daylight are now seeing sunset times pushed significantly later and sunrise times moved earlier, creating nearly continuous daylight conditions that affect ecosystems not adapted to handle such extreme light exposure. Temperature measurements from across the Arctic show that midnight sun periods are becoming not just longer but significantly hotter. The continuous solar energy input during 24-hour daylight creates feedback loops where heated air and land surfaces retain warmth throughout what should be the cooler nighttime hours. This perpetual heating accelerates ice melt, changes local weather patterns, and creates temperature extremes that stress both human communities and natural ecosystems. Researchers monitoring polar regions throughout 2025 documented midnight sun intensities that exceeded measurements from previous decades. Solar radiation meters placed across northern Canada, Greenland, and Siberia recorded continuous energy inputs that reached levels typically associated with tropical regions, but sustained over periods of months rather than single days. This intense and prolonged solar exposure is transforming Arctic landscapes at unprecedented rates. The ancient cosmic collision that tilted our planet is creating modern conditions that push the boundaries of what human communities and natural ecosystems can endure. But the same 23-degree angle that creates months of endless daylight in the Arctic also drives some of the most violent weather phenomena on Earth, generating atmospheric conditions so powerful they can level entire communities in a matter of minutes. Tornado alleys, deadly migration across America. These same atmospheric forces now drive tornadoes along paths that defy every prediction meteorologists have relied on for decades. The deadliest tornadoes in American history have always followed predictable routes through the Great Plains, carving destruction through Texas, Oklahoma, Kansas, and Nebraska in a region known as Tornado Alley. For decades, families living outside this zone felt relatively safe from the rotating storms that claim dozens of lives each year. But 2025 shattered that sense of security as violent tornadoes began appearing in places they had never struck before, catching entire communities completely unprepared. The 2025 tornado season produced catastrophic results that left meteorologists scrambling to understand what had changed. On April 15, an EF4 tornado with winds exceeding 180 miles per hour tore through southeastern Pennsylvania, killing 23 people and destroying over 400 homes in an area where no tornado of that magnitude had ever been recorded. 3 weeks later, another massive tornado struck central Virginia, producing damage that exceeded anything the region had experienced in recorded history. By the end of May, traditionally low-risk states like North Carolina, Tennessee, and even parts of New York had reported tornado activity that matched or exceeded typical Great Plains statistics. The mechanism that creates these devastating storms depends entirely on Earth's 23-degree tilt and the seasonal temperature contrasts it generates across North America. Tornadoes form when warm, moist air masses collide with cold, dry air masses under specific atmospheric conditions. The tilt creates these contrasting air masses by heating the southern United States much more intensely than northern regions during spring and summer months. As warm air from the Gulf of Mexico flows northward, it encounters cold Canadian air moving south, creating the temperature boundaries where tornadoes develop. Climate data from 2025 reveals that this ancient stability is breaking down as changing atmospheric conditions shift the jet stream into entirely new patterns. The river of fast-moving air that normally flows straight across the continent began meandering wildly throughout the spring of 2025, dipping far south into Mexico before swinging dramatically north into Canada. These wild fluctuations created temperature collisions in regions that had never experienced the atmospheric conditions necessary for severe tornado development. Storm chaser teams that spent decades following tornadoes through traditional Tornado Alley found themselves racing toward states they had never visited for tornado research. Marcus Rodriguez, who has documented severe weather for 15 years, spent April and May of 2025 chasing storms through Virginia, Maryland, and southern New Jersey instead of his usual routes through Oklahoma and Kansas. The tornado signatures he measured using portable radar equipment matched the intensity of classic Great Plains supercells, but they were occurring in landscapes and communities with no historical experience of such extreme weather. Regional tornado frequency data from 2025 shows increases that stunned meteorologists across multiple states outside traditional tornado zones. Maryland recorded 15 confirmed tornadoes during the peak season compared to its historical average of 3 per year. Virginia documented 28 tornadoes, more than double its previous record of 13 set in 2004. Pennsylvania experienced 22 confirmed tornadoes, exceeding its typical annual total of 8 to 10 events. These weren't weak tornadoes either. Many reached EF2 and EF3 intensity levels, capable of destroying well-built homes and killing people caught without adequate shelter. Emergency management officials in affected regions admitted they were completely unprepared for tornado threats that had never existed in their jurisdictions before. Most homes and buildings in the Southeast and Mid-Atlantic states lack basements or storm shelters because tornadoes were never considered a significant risk. Schools, hospitals, and government buildings had emergency plans for hurricanes and winter storms, but no protocols for tornado warnings that residents had never heard before. The National Weather Service issued more tornado watches and warnings for non-traditional states during the first 6 months of 2025 than in the previous 5 years combined. Weather forecasters found themselves explaining tornado safety procedures to television audiences who had never needed to know the difference between a watch and a warning. Local emergency management agencies conducted tornado drills in communities where such preparations had seemed unnecessary just years earlier. Traditional tornado safety maps that insurance companies and emergency management agencies have used for decades are becoming dangerously unreliable as the zones of highest tornado risk shift eastward. FEMA risk assessments, building codes, and disaster preparedness funding are all based on historical tornado patterns that no longer reflect current atmospheric conditions. Communities that invested in hurricane preparedness are finding they need completely different infrastructure to protect residents from rotating storms. Meteorologists studying these shifting patterns cannot predict with certainty which regions will experience increased tornado activity in coming years. The interaction between Earth's tilt and changing jet stream behavior creates complex atmospheric dynamics that current forecasting models struggle to anticipate more than a few days in advance. What seems certain is that the geographic boundaries of tornado risk are expanding beyond their historical limits, putting millions of Americans in danger from storms their communities were never designed to survive. But tornadoes represent just one type of weather system that Earth's tilted orientation controls. The same 23-degree angle that drives these violent rotating storms also powers much larger atmospheric phenomena that sustain entire civilizations across multiple continents. The monsoon systems that feed billions are failing. These massive atmospheric systems control the survival of over 2 billion people who depend on seasonal monsoon rains that arrive with clockwork precision every year. These colossal weather events deliver the water that grows rice in India, feeds livestock in East Africa, and sustains entire civilizations that have organized their lives around predictable seasonal flooding for thousands of years. But 2025 brought monsoon failures and chaotic rainfall patterns that left vast regions without the life-giving water they desperately needed, creating agricultural disasters that threatened food security for nearly a third of the world's population. The monsoon represents one of Earth's most spectacular demonstrations of how our planet's 23-degree tilt creates the weather systems that sustain human civilization. These seasonal rain events happen because the tilt causes massive landmasses to heat up dramatically during summer months while nearby oceans remain relatively cool. This temperature difference creates enormous pressure variations that literally suck moisture-laden air from the oceans onto the land, producing months of intense precipitation that can deliver more water in a few weeks than other regions receive in entire years. During summer months, the sun beats down on huge landmasses like the Indian subcontinent and eastern Africa, heating the ground to temperatures that create rising air currents and low-pressure zones. Meanwhile, the surrounding oceans absorb solar energy more slowly, maintaining higher atmospheric pressure that pushes moisture-rich air toward the heated land. This pressure difference acts like a massive atmospheric pump that draws water vapor inland for hundreds of miles, creating the seasonal deluges that farmers have relied on for millennia. Agricultural regions across India experienced catastrophic monsoon disruptions throughout 2025 that exceeded anything in recent memory. The vital summer monsoon that typically arrives in Kerala during late May and sweeps across the subcontinent through September arrived more than 3 weeks late in many areas and delivered irregular rainfall patterns that left farmers unable to predict when to plant their crops. Rice paddies that should have been flooded with consistent water levels instead experienced alternating periods of drought and excessive flooding that destroyed seedlings and contaminated soil with salt deposits. Maharashtra state, which produces significant portions of India's sugarcane and cotton crops, recorded monsoon rainfall that fell 40% below normal levels during the crucial July and August growing period. The delayed and insufficient rains forced farmers to rely on groundwater irrigation that depleted aquifers already stressed by previous dry years. Cotton crops that depend on specific moisture levels during flowering stages suffered widespread failures as irregular rainfall created growing conditions that prevented proper fiber development. Similar monsoon disruptions devastated agricultural communities across multiple continents throughout 2025, creating a global pattern of seasonal rainfall failures that scientists had never observed simultaneously before. West Africa's monsoon system, which typically brings essential precipitation to countries like Mali, Burkina Faso, and Niger during the summer months, delivered erratic rainfall that caused both droughts and floods within the same growing season. Millet and sorghum crops that feed millions of people across the Sahel region failed as farmers struggled to adapt planting schedules to rainfall patterns that changed unpredictably from week to week. The East African monsoon experienced equally severe disruptions that affected food production across Ethiopia, Kenya, and Somalia. The long rains that typically occur from March through May arrived sporadically and ended abruptly, leaving maize and bean crops without adequate water during critical growth periods. Pastoralist communities that depend on seasonal grass growth for livestock grazing found themselves facing feed shortages that forced them to sell cattle and goats at drastically reduced prices, destroying economic foundation that had sustained these societies for generations. Climate scientists studying these widespread monsoon failures discovered that changing ocean temperatures are fundamentally altering how Earth's tilt creates the pressure differences that drive these massive weather systems. Sea surface temperatures in the Indian Ocean during 2025 remained higher than historical averages throughout the monsoon season, reducing the temperature contrast between land and sea that generates the atmospheric pressure gradients necessary for strong monsoon circulation. This weakened pressure difference meant that moisture-laden air lacked the driving force needed to penetrate far inland, leaving interior agricultural regions without their expected seasonal water supply. The cascading effects of monsoon disruption extended far beyond individual farming communities to affect global food markets and supply chains that depend on predictable crop production from monsoon-dependent regions. Rice prices in international markets increased by 35% during the latter half of 2025 as Indian production fell short of export commitments, forcing importing countries to seek alternative suppliers or reduce consumption. Spice markets experienced similar volatility as cardamom, pepper, and turmeric crops in monsoon-dependent growing regions produced yields that fell 20 to 50% below normal levels. Rural communities across monsoon-dependent regions faced humanitarian crises as traditional farming practices failed to provide adequate food security for families that had relied on predictable seasonal patterns for their entire lives. Smallholder farmers who invested their limited resources in seeds and labor based on expected monsoon timing found themselves unable to recover costs when crops failed due to irregular rainfall. Many families exhausted savings and borrowed money to survive the growing season, creating debt burdens that will affect their communities for years to come. Traditional weather forecasting methods that worked reliably for centuries are becoming useless as the fundamental relationship between Earth's tilt and monsoon generation changes in response to warming oceans and altered atmospheric circulation patterns. The seasonal heating cycles that create monsoon systems are no longer producing the reliable pressure differences that billions of people depend on for their survival. These disruptions reach far beyond the regions where monsoons fail, affecting every aspect of how food reaches tables around the world. Your food supply's hidden dependence on planetary tilt. The breakfast cereal in your bowl, the coffee beans that fuel your morning, and the vegetables in your lunch salad all exist because of a cosmic accident that happened 4.5 billion years ago. Every single meal you eat depends on Earth's 23-degree tilt in ways that most people never realize. This ancient planetary orientation controls when crops can be planted, how long they have to grow, and whether they'll survive to harvest. But 2025 revealed that the growing seasons our entire food system depends on are becoming dangerously unpredictable. The connection between Earth's tilt and your dinner plate operates through growing seasons that determine what foods can be produced where and when. Every crop has specific temperature and daylight requirements that must be met during critical growth periods, and these requirements are satisfied only because our tilted planet creates predictable seasonal changes. Wheat needs cool temperatures during germination, followed by warm conditions during grain development. Corn requires consistent warmth and specific daylight hours during pollination. Rice depends on flooding during planting season, followed by dry conditions during harvest. These precise seasonal requirements evolved over thousands of years as farmers developed crop varieties that matched the predictable climate patterns created by Earth's tilt. Agricultural societies organized their entire calendar around planting dates, growing seasons, and harvest times that aligned with the seasonal temperature and precipitation cycles. This agricultural timing became so reliable that civilizations built their economic systems, trade networks, and population centers around the assumption that specific crops would be ready at specific times every year. Agricultural zone mapping data from 2025 reveals dramatic shifts in where different crops can be successfully grown as traditional growing seasons become unreliable. The USDA Plant Hardiness Zone Map, which farmers use to determine what crops will survive in their region, experienced changes in 2025 that exceeded the shifts typically seen over entire decades. Zones that had remained stable for 50 years moved northward by distances equivalent to 100 to 150 miles, forcing farmers to completely reconsider what crops they could plant. Corn production across the Midwest faced unprecedented challenges as traditional planting schedules became misaligned with actual weather conditions. Farmers in Iowa and Illinois typically plant corn between April 15 and May 15, timing that evolved to match soil temperature and moisture conditions created by Earth's seasonal patterns. But 2025 brought soil conditions in mid-March that resembled typical late April weather, followed by unexpected late frosts in May that killed seedlings planted according to historical timing. The result was corn yields that fell 23% below normal levels across major producing states. Wheat farmers experienced equally disruptive seasonal timing problems that threatened one of humanity's most important food sources. Winter wheat planted in Kansas and Oklahoma during fall 2024, according to traditional timing schedules, faced spring weather patterns that arrived weeks early, causing plants to begin growth before they had received adequate cold exposure for proper grain development. The premature warming disrupted the vernalization process that winter wheat requires, resulting in reduced yields and lower protein content that made much of the harvest unsuitable for bread production. Apple orchards across New England and the Pacific Northwest struggled with flowering periods that no longer matched historical patterns. Apple trees require specific combinations of winter chilling hours followed by warm spring temperatures to produce fruit. But 2025 brought warming periods that triggered blooming before the last frost date had passed. Late-season freezes killed apple blossoms across thousands of acres, destroying fruit production and forcing orchards to operate at severe economic losses. The global food distribution system depends on predictable harvest timing from different regions around the world to maintain consistent food supplies throughout the year. When seasonal disruptions affect planting and harvest schedules simultaneously across multiple continents, the entire network of food production and distribution faces severe strain. Countries that typically import fresh fruits and vegetables from specific regions during certain months found their suppliers unable to deliver products when expected. Food price volatility in 2025 reflected the direct connection between Earth's tilted seasonal patterns and grocery store costs that consumers pay daily. Avocado prices increased by 40% during summer months as Mexican growing regions experienced irregular rainfall that reduced fruit production. Bell pepper costs doubled in September as California crops failed due to extended heat waves that prevented proper fruit development. Wheat-based products saw price increases of 25 to 30% as global wheat production fell short of demand due to seasonal timing disruptions. Indigenous communities across Canada reported that climate change is disrupting traditional hunting, fishing, and gathering practices, as unpredictable weather patterns and shifting migration routes challenge food systems that have sustained these populations for thousands of years. Warmer weather in northern Manitoba is causing ice roads to deteriorate, impacting food security and travel access to traditional hunting grounds. Our modern food system assumes that Earth's 23-degree tilt will continue creating the same seasonal patterns that have sustained agriculture for thousands of years. Every aspect of food production, from seed development to distribution networks, is built around the expectation that spring will arrive at predictable times, growing seasons will last for consistent durations, and harvest periods will align with processing and storage capacity. The seasonal chaos of 2025 demonstrated that these fundamental assumptions may no longer be reliable. But the most dramatic evidence of how our tilted planet is responding to climate change isn't happening in farm fields or grocery stores. It's occurring at the ends of the Earth, where seasonal temperature extremes are creating changes so rapid that scientists initially refused to believe their own measurements. The polar ice melt that's accelerating beyond all predictions. At the planet's frozen extremes, polar ice vanished at rates in 2025 that left climate scientists staring at data they initially thought must be measurement errors. Glaciers that had existed for thousands of years completely disappeared within single summer seasons. Ice sheets that scientists expected would take decades to retreat instead collapsed in months. The speed of polar ice loss exceeded even the most pessimistic climate projections by margins so large that researchers had to recalibrate their understanding of how quickly Earth's frozen regions can transform. Earth's 23-degree tilt acts like a massive solar concentrator at the poles, focusing intense sunlight on regions covered in reflective ice during summer months. When our planet tilted sideways billions of years ago, it created seasonal extremes that are most dramatic at the North and South poles. During polar summer, the sun shines continuously for months, pouring solar energy onto ice surfaces that have no nighttime cooling periods to provide relief from the constant heating. In polar regions, summer means the sun traces a circular path around the sky without ever setting, delivering solar radiation 24 hours per day for months at a time. Unlike temperate regions where nighttime temperatures provide cooling that slows ice melt, polar ice faces relentless heating with no recovery periods. The white ice surfaces that normally reflect solar energy back to space become less effective as they develop surface water from melting, which absorbs more heat and accelerates the melting process. Temperature swings in polar regions during 2025 reached levels that shattered records dating back to the beginning of reliable measurements. Arctic weather stations recorded summer temperatures that exceeded historical averages by 8 to 12 degrees Celsius during peak melting periods. These extreme temperatures occurred not just for single days, but sustained over weeks and months, creating conditions that overwhelmed the ice's ability to maintain structural integrity. Arctic sea ice extent hit record low levels for much of June and into early July 2025, remaining well below the historical range established between 1979 and 2010. The ice cover that normally persists year-round in the central Arctic Ocean developed massive open water areas that had never appeared in satellite records. These ice-free zones absorbed solar energy that would normally be reflected back to space, creating feedback loops that accelerated warming throughout the entire Arctic region. The 2025 melting season extended far beyond its traditional time boundaries, as changing seasonal patterns prolonged the period when temperatures remained above freezing. Arctic researchers documented melting activity continuing through September and into October, months when ice formation should have begun. The extended melting season meant that ice had less time to rebuild during winter months, creating cumulative losses that compounded year after year. Greenland's ice sheet experienced mass loss events throughout 2025 that occurred simultaneously across the entire landmass, something researchers had never observed before. Satellite measurements showed surface melting occurring at elevations above 10,000 feet, regions that had remained frozen even during the warmest previous years. The ice sheet lost an estimated 280 billion tons of ice during the 2025 melting season, equivalent to enough water to raise global sea levels by nearly 1 millimeter in a single year. Dr. Sarah Mitchell, a glaciologist who has studied Arctic ice for 20 years, witnessed changes in 2025 that exceeded anything in her career. We're watching ice formations that took centuries to build disappear in real time. Glaciers I've monitored for decades simply don't exist anymore. The rate of change is so rapid that our measurement equipment can barely keep up with documenting what's happening. Time-lapse photography from research stations across Greenland and the Canadian Arctic captured glacial retreat that appeared to accelerate throughout the summer months. Glaciers that typically retreated a few meters per year instead pulled back hundreds of meters in weeks. The Jakobshavn Glacier in Greenland, one of the fastest-moving glaciers in the world, increased its flow rate to speeds that exceeded previous measurements by 40%. Dumping massive amounts of ice into the ocean at unprecedented rates. The tilt-driven seasonal extremes create feedback loops that amplify warming effects far beyond what the increased solar energy alone would produce. As ice melts, it exposes darker land and water surfaces that absorb more solar radiation instead of reflecting it back to space. This absorbed energy heats the surrounding area, melting more ice and creating a self-reinforcing cycle that accelerates with each degree of warming. The 23-degree tilt concentrates this feedback process during the continuous daylight of polar summer, when there are no cooling periods to interrupt the heating cycle. Sea level rise measurements from 2025 showed acceleration that caught coastal monitoring systems unprepared for the rapid changes. Tide gauges along the eastern seaboard of the United States recorded water level increases that exceeded annual averages within single months. Miami experienced king tide flooding that reached levels previously projected for 2030, while Norfolk, Virginia, documented sea level rise rates that exceeded the most aggressive scientific projections by significant margins. The polar ice melt documented in 2025 represents a fundamental shift in how Earth's frozen regions respond to seasonal heating created by our planet's ancient tilt. The combination of continuous summer sunlight and warming temperatures created conditions that overwhelmed the ice's ability to maintain stability, triggering collapse rates that exceeded scientific projections. But the disruption of Earth's ancient seasonal rhythms extends far beyond melting ice, affecting biological systems that have depended on predictable timing for millions of years. Animal migration chaos disrupting entire ecosystems. Millions of animals worldwide are arriving at destinations where their survival depends on timing that no longer exists. Arctic terns flying from Arctic breeding grounds to Antarctic feeding areas reach their destinations weeks late to find that expected food sources have already disappeared. Caribou herds in Alaska wander in circles instead of following traditional routes to winter feeding grounds. Monarch butterflies that should reach Mexico in November are still struggling through Texas in December, their internal navigation systems apparently broken. These widespread migration failures reveal how deeply Earth's 23-degree tilt controls the biological rhythms of virtually every animal species on the planet. Animals don't migrate randomly or based on conscious decisions. They respond to seasonal cues created by our tilted planet as it orbits the sun, using changes in daylight duration, temperature patterns, and food availability as precise timing signals that have remained consistent for thousands of generations. These environmental cues trigger hormonal changes that compel animals to begin their journeys at exactly the right moments to arrive. when conditions are optimal for survival and reproduction. Migration timing evolved over millions of years as animals developed internal biological clocks synchronized with Earth's seasonal patterns. Birds measure changing daylight hours to determine when to begin long-distance flights. Marine animals track water temperature shifts that signal the start of feeding season. Land mammals respond to plant growth cycles that indicate when food sources will be available along migration routes. This intricate timing system worked perfectly when seasonal patterns remained predictable and consistent year after year. But 2025 shattered this ancient synchronization as animals arrived at destinations weeks or even months before or after their food sources, breeding partners, or suitable habitat conditions became available. Gray whales traveling along the Pacific coast reached their Alaska feeding grounds in early May instead of late June, arriving before the zooplankton blooms they depend on had developed. The whales found empty waters where massive food concentrations should have been waiting, forcing them to continue searching for nutrition while burning energy reserves they needed for the return journey south. Bird migration disruptions in 2025 created some of the most visible examples of how changing seasonal cues confuse animal navigation systems. Warbler species that typically arrive in northern breeding territories precisely when insect populations peak instead showed up weeks before their food sources emerged from winter dormancy. The birds faced starvation in environments where they expected abundant feeding opportunities, forcing many to attempt dangerous return flights to find alternative food sources. Swallow populations across Europe experienced similar timing disasters, as insects they depend on emerge according to different seasonal schedules than the birds' arrival times. The birds evolved to time their migration, so they would arrive just as flying insects became plentiful. But temperature changes caused insect emergence to shift earlier, while the birds continued following traditional migration schedules. This mismatch left swallow populations without adequate food during critical breeding periods, when they need maximum nutrition to produce eggs and feed their young. Whale migration patterns documented throughout 2025 revealed how marine animals are struggling with disrupted seasonal cues that no longer align with ocean conditions. Humpback whales that normally time their Alaska to Hawaii migration to coincide with specific water temperatures found themselves traveling through unusually warm or cold ocean zones that affected their ability to navigate and find food. Many whale populations arrived at traditional feeding areas to discover that changing ocean temperatures had shifted the distribution of krill and other food sources they expected to find. The biological clock disruption extends beyond individual species to affect entire ecosystems that depend on precisely timed interactions between different animals. Predator species evolved to arrive at hunting grounds exactly when their prey animals would be most abundant and vulnerable. But when prey species arrive weeks early or late due to confused seasonal cues, predators find themselves in locations where their expected food sources are absent, creating food chain breakdowns that cascade through entire ecosystems. Mass animal die-offs documented in 2025 provided stark evidence of how migration disruption leads to population collapses. Seabird colonies in the North Atlantic experienced breeding failures when fish populations they depend on shifted their seasonal movements earlier than the birds' egg-laying schedules. Parent birds couldn't find adequate food to feed their chicks, resulting in widespread nest abandonment and juvenile mortality that reduced entire colony populations by 30 to 50%. Caribou herds across northern Canada wandered aimlessly through landscapes where traditional food sources had already been consumed by other animals or hadn't yet become available due to altered plant growth cycles. The confusion caused herd fragmentation as different groups of animals responded to conflicting environmental signals, breaking up migration patterns that had kept populations together for thousands of years. Many individual animals became separated from their herds and died during harsh weather conditions. They would normally survive by staying with the group. The cumulative effect of migration disruptions across multiple species creates ecosystem instability that threatens biodiversity on a global scale. When pollinating animals arrive after flowers have finished blooming, plant reproduction fails and affects seed production for the following year. When seed-dispersing animals miss their traditional timing, forest regeneration patterns change and affect habitat availability for other species. These interconnected disruptions multiply through food webs and create conditions where entire ecosystems lose their ability to function normally. The migration chaos observed in 2025 represents early evidence that Earth's changing seasonal patterns could trigger ecosystem collapses on a scale that rivals previous mass extinction events. When billions of animals can no longer successfully complete the migrations that have sustained their populations for millions of years, the resulting biodiversity loss creates cascading effects that fundamentally alter life on Earth. But these same disrupted seasonal rhythms that confuse animal migration patterns are also affecting another species that evolved to depend on predictable seasonal changes: humans themselves. Human health impacts you never saw coming. Your body responds to these disrupted seasonal patterns with symptoms that most doctors never learned to connect to planetary mechanics. The persistent fatigue, unexplained mood swings, and disrupted sleep cycles that millions of people experienced throughout 2025 weren't coincidental health problems. They were direct consequences of how Earth's 23-degree tilt controls human biology through seasonal light patterns that shifted too rapidly for internal biological systems to adapt. Human biology depends entirely on seasonal light exposure patterns created by our planet's tilted orientation as it orbits the sun. The amount of daylight your eyes receive each day triggers hormonal responses that control everything from sleep cycles to immune system function. Your pineal gland produces melatonin based on darkness exposure, while your thyroid adjusts metabolism according to seasonal temperature changes. Your adrenal glands modify stress hormone production based on daylight duration variations that signal whether to prepare for active summer months or slower winter periods. This biological programming assumes seasonal changes will follow consistent patterns year after year. But 2025 brought light exposure variation that confused the human endocrine system across multiple continents. Daylight duration changes that normally occur gradually over months instead happened within weeks, creating hormonal disruption that left people feeling exhausted, anxious, and unable to maintain normal sleep schedules. The human body cannot adjust its internal clock fast enough to handle seasonal pattern changes occurring at unprecedented speeds. Medical data from 2025 documents dramatic increases in seasonal affective disorders, circadian rhythm disruption, and sleep disturbances that coincided directly with irregular seasonal light patterns. Hospital emergency departments reported 40% increases in patients seeking treatment for severe insomnia during months when daylight hours shifted more dramatically than historical averages. Sleep disorder clinics experienced waiting lists extending for months as people struggled with disrupted sleep cycles that traditional treatments couldn't resolve. Mental health statistics from 2025 reveal connections between seasonal disruption and psychological disorders, extending far beyond typical seasonal depression. Anxiety disorder diagnoses increased by 35% in regions experiencing the most dramatic seasonal pattern changes, while panic attack incidents rose nearly 50% during periods when daylight duration shifted most rapidly. Depression rates climbed significantly even in southern regions that had never experienced high levels of seasonal mood disorders in previous years. The disruption affects vitamin D production in ways that create cascading health problems throughout the human body. Vitamin D synthesis depends on specific wavelengths of sunlight reaching skin during optimal sun angles that occur predictably throughout normal seasonal cycles. When seasonal patterns shift dramatically, people miss the sun exposure windows their bodies expect for adequate vitamin D production, leading to deficiencies that affect bone health, immune function, and cardiovascular systems. Hormone cycle disruption extends beyond sleep and mood regulation to affect reproductive health, metabolic function, and immune system responses. Women reported menstrual cycle irregularities that coincided with disrupted seasonal light patterns, while both men and women experienced thyroid function changes affecting energy levels and weight regulation. The human endocrine system evolved to anticipate seasonal changes and prepare the body accordingly, but unpredictable seasonal timing leaves hormonal systems unable to maintain proper balance. Sleep architecture studies conducted during 2025 showed measurable changes in how people progress through different sleep stages when exposed to irregular seasonal light patterns. Rapid eye movement sleep decreased significantly during periods of dramatic daylight duration changes, while deep sleep stages became fragmented and less restorative. These sleep quality changes affected cognitive function, emotional regulation, and physical recovery in ways that created persistent health problems extending far beyond simple tiredness. Immune system function declined measurably in populations experiencing the most severe seasonal disruption throughout 2025. White blood cell production patterns that normally adjust seasonally to prepare for typical cold and flu seasons instead became erratic and unpredictable. People experienced more frequent infections, slower healing times, and autoimmune responses that suggested their immune systems were struggling to maintain proper seasonal adjustment cycles. Children showed particularly severe responses to seasonal disruption, as their developing biological systems proved less adaptable to irregular light exposure patterns. Pediatric sleep disorder diagnoses increased by 60% in regions with the most dramatic seasonal changes, while attention deficit symptoms rose significantly in school-age children during periods of rapid daylight duration shifts. The developing brain appears especially vulnerable to seasonal timing disruption that interferes with normal neural development patterns. Public health surveillance data from 2025 documents population-level health trends that correlate directly with seasonal pattern disruption across multiple geographic regions. Cities experiencing the most irregular seasonal timing showed increased hospital admissions for mood disorders, sleep disturbances, and hormone-related health problems. Emergency department visits for anxiety and panic disorders peaked during weeks when daylight hours changed, most dramatically compared to historical seasonal patterns. The broader implications extend beyond individual symptoms to affect workplace productivity, traffic accident rates, and healthcare system capacity. Absenteeism increased significantly in regions experiencing severe seasonal disruption as people struggled with fatigue, mood disorders, and sleep problems that interfered with normal daily functioning. Motor vehicle accidents rose during periods of rapid seasonal change, as disrupted circadian rhythms affected driver alertness and reaction times. Human evolution occurred over millions of years, during which seasonal patterns remained remarkably stable and predictable. Our biological systems developed intricate timing mechanisms that depend on consistent seasonal cues to maintain optimal health and function. The rapid seasonal changes documented in 2025 represent environmental conditions that human physiology has never encountered before, creating health challenges that exceed our species' ability to adapt through normal biological processes. But these widespread health impacts represent only the beginning of how seasonal disruption affects human society. as the true costs extend far beyond medical bills into every aspect of how our economy functions. The economic catastrophe hidden in seasonal shifts. Insurance companies discovered their risk models became worthless overnight when seasonal disaster patterns shifted beyond historical precedent. Property claims in 2025 exceeded company reserves by margins that threatened major insurers' solvency. Tornado damage from regions that never experienced significant tornado activity overwhelmed companies that calculated premiums based on risk patterns that no longer apply. Modern economic systems built themselves around the assumption that Earth's 23-degree tilt would create identical seasonal patterns forever. Entire industries structured business models, supply chains, and financial planning around seasonal cycles consistent for thousands of years. Tourism companies schedule operations based on predictable weather patterns. Energy utilities plan capacity and pricing around seasonal heating and cooling demands. Agricultural markets time planting, harvesting, and distribution to match expected seasonal conditions. Economic losses from seasonal disruption in 2025 reached levels that stunned financial analysts who had never calculated the true cost of unstable seasonal patterns. The agricultural sector alone suffered an estimated $180 billion in losses as irregular growing seasons destroyed crops, disrupted planting schedules, and forced farmers to replant fields multiple times. Food processing companies lost an additional $45 billion when seasonal timing disruptions prevented them from receiving raw materials when production schedules required them. Energy companies faced catastrophic financial losses as seasonal heating and cooling demands shifted dramatically from historical patterns. Utility companies in the northeastern United States recorded heating fuel purchases that exceeded winter budgets by 35% when unexpected cold periods extended well beyond normal winter months. Meanwhile, southwestern utilities faced air conditioning demands during traditionally mild months that overwhelmed electrical grid capacity, designed around predictable seasonal load patterns. The tourism industry experienced economic devastation as seasonal weather patterns no longer matched conditions that attract visitors to specific destinations during traditional peak seasons. Ski resort operators across Colorado and Utah lost an estimated $2.8 billion in 2025 when warm weather prevented adequate snow accumulation during prime skiing months. Beach resort destinations faced similar losses when unusual weather patterns drove away visitors who expected predictable seasonal conditions. Supply chain disruptions created cascading economic effects that multiplied losses across interconnected industries. Manufacturing companies faced production shutdowns when agricultural raw materials arrived weeks late due to seasonal timing disruptions. Shipping companies struggled to maintain delivery schedules when seasonal weather patterns no longer matched logistical planning assumptions. Retail companies faced inventory shortages and excess stock problems when seasonal consumer demand patterns shifted dramatically from historical trends. Employment effects from seasonal economic disruption reached beyond individual job losses to create regional economic collapse in areas heavily dependent on seasonal industries. Agricultural regions faced unemployment rates exceeding 25% as farming operations failed due to unpredictable seasonal conditions. Tourism-dependent communities experienced similar economic devastation when seasonal visitor patterns collapsed due to unreliable weather conditions that drove away traditional customers. Financial markets responded to seasonal economic disruption, with volatility reflecting widespread uncertainty about how to value companies whose business models depend on predictable seasonal patterns. Agricultural commodity futures markets experienced price swings that exceeded normal trading ranges by 200 to 300%, as investors struggled to predict crop yields under unstable seasonal conditions. Energy company stock prices fluctuated wildly, as utility demand patterns became impossible to forecast accurately. Banking systems faced stress as loan defaults increased dramatically in regions affected by seasonal economic disruption. Agricultural loans became uncollectible when farmers couldn't harvest crops due to irregular seasonal timing. Small business loans defaulted when seasonal customer patterns shifted away from predictable demand cycles that business owners had relied on for decades. Home mortgages entered foreclosure at increased rates as regional economic collapse eliminated employment opportunities in seasonally dependent industries. Regional case studies from 2025 demonstrate how seasonal economic collapse triggered broader social problems, extending far beyond financial losses. Rural communities in Kansas and Nebraska experienced population exodus as agricultural failures destroyed the economic foundation that sustained local businesses, schools, and healthcare facilities. Small towns that survived for generations lost essential services when seasonal economic disruption eliminated agricultural income that supported their tax base and local economy. Global financial institutions recognize that seasonal economic disruption represents a systemic risk that could trigger international financial instability. The interconnected nature of modern economies means seasonal economic collapse in agricultural regions affects food prices worldwide. Energy market disruption in major producing regions creates price volatility, affecting transportation costs globally. Tourism industry failures in major destinations impact international travel and hospitality sectors across multiple countries. Economic modeling from 2025 suggests that continued seasonal disruption could cost the global economy between $2.5 and $4.2 trillion annually if current trends continue. These projections account for agricultural losses, energy sector disruption, tourism industry decline, insurance market instability, and cascading effects across interconnected economic sectors. The calculations reveal that seasonal economic disruption represents one of the largest potential threats to global financial stability in the modern era. The economic catastrophe demonstrates how a cosmic accident from 4.5 billion years ago continues controlling modern financial systems in ways most people never realize. When Earth's ancient tilt stops creating predictable seasonal patterns, the economic consequences threat to reshape global prosperity and financial stability fundamentally. But the massive disruptions witnessed in 2025 may represent only the beginning of how our tilted planet will transform the world we know. What 2026 and beyond hold for our tilted planet? Scientific projections for the coming years reveal acceleration patterns that could make 2025's disruptions appear modest by comparison. Climate models incorporating Earth's 23-degree tilt effects suggest that seasonal temperature swings will become more extreme as greenhouse gas concentrations continue rising in the atmosphere. The tilt acts as an amplifier for temperature changes, meaning that even small increases in global average temperatures create dramatically larger seasonal variations in many regions. Computer simulations indicate that the jet stream disruptions observed in 2025 will likely become more frequent and severe as temperature gradients between the equator and poles continue shifting. These atmospheric changes will push seasonal weather patterns into regions that have never experienced such conditions before. The models suggest that by 2030, traditional seasonal boundaries could shift northward by distances equivalent to 200 to 400 miles, forcing entire ecosystems and human communities to adapt to completely different seasonal cycles. Regions at higher latitudes face the greatest vulnerability to future tilt-related changes, as polar amplification continues accelerating warming in Arctic and subarctic areas. Northern Canada, Alaska, Greenland, and northern Scandinavia will experience the most dramatic seasonal disruptions as continuous summer sunlight created by Earth's tilt interacts with rapidly warming atmospheric conditions. These regions could see seasonal temperature increases that exceed global averages by factors of 3 to 5 times. Tropical and subtropical regions will face different but equally challenging seasonal disruptions as changing atmospheric circulation patterns alter monsoon systems and hurricane formation cycles. Countries across Southeast Asia, Central Africa, and parts of South America that depend on predictable seasonal rainfall could experience increasingly erratic precipitation patterns that threaten agricultural systems supporting billions of people. Understanding how Earth's tilt creates these seasonal patterns provides essential knowledge for preparing communities to handle upcoming disruptions. Local governments can use seasonal prediction models to adjust infrastructure planning for temperature extremes that exceed historical ranges. Agricultural regions can develop crop rotation strategies that account for shifting growing seasons and unpredictable weather timing. Coastal communities can prepare for sea level changes, accelerated by tilt-driven polar ice melt. Emergency management systems require complete overhaul to address seasonal disasters occurring in regions that never faced such threats before. Tornado preparedness programs must expand into southeastern states, where rotating storms are becoming more common. Flood management systems need upgrading in areas where changing seasonal precipitation patterns create unexpected water management challenges. Wildfire prevention strategies require adaptation for regions where altered seasonal drying periods extend fire risk into months that were previously considered safe. Emerging technologies show promise for helping communities adapt to seasonal chaos created by Earth's tilted orientation. Advanced weather prediction systems using satellite data and atmospheric modeling can provide earlier warnings when seasonal patterns begin shifting dramatically. Precision agriculture technologies allow farmers to adjust planting schedules based on real-time soil and weather conditions rather than relying on historical seasonal timing. Smart grid electrical systems can better handle seasonal energy demand fluctuations as heating and cooling patterns become less predictable. Expert opinions remain divided on whether seasonal patterns might eventually stabilize or continue becoming more extreme over the coming decades. Some climate scientists suggest that atmospheric conditions could reach a new equilibrium where seasonal patterns become predictable again, although different from historical norms. Other researchers warn that feedback loops between Earth's tilt effects and warming temperatures could create permanently chaotic seasonal behavior that never stabilizes into recognizable patterns. Individual actions connect directly to broader societal adaptation efforts that could determine how successfully human civilization adjusts to seasonal disruption. Supporting renewable energy development reduces greenhouse gas emissions that amplify tilt-driven seasonal extremes. Advocating for climate adaptation funding helps communities prepare infrastructure for changing seasonal conditions. Choosing locally grown food reduces dependence on agricultural systems, vulnerable to seasonal disruption in distant regions. Personal preparedness strategies become increasingly important as seasonal predictability continues declining. Households can develop emergency supply plans that account for unexpected seasonal disasters in their regions. Home energy efficiency improvements reduce vulnerability to seasonal heating and cooling cost spikes. Community involvement in local adaptation planning helps ensure neighborhoods are prepared for seasonal changes that affect entire regions. Climate projections suggest there is a 43% chance that 2025 will exceed the 1.5 degrees Celsius warming threshold that climate scientists consider a critical tipping point for Earth's climate system. This probability indicates that seasonal disruption could intensify significantly in coming years, as atmospheric conditions cross thresholds that trigger more dramatic responses to Earth's tilted orientation. The path forward depends on recognizing that seasonal chaos represents one of the most fundamental threats to human prosperity in the modern era. Whether humanity successfully adapts to this challenge requires understanding that every weather disaster, agricultural failure, and economic disruption stems from the same ancient source that has controlled our planet's behavior for billions of years. Now you understand the hidden force that shapes your daily existence in ways you never imagined. A single moment of cosmic violence 4.5 billion years ago created the tilted world that generated every weather disaster, seasonal disruption, and climate challenge you witnessed in 2025. That ancient collision between Earth and planet Theia continues reshaping our lives through mechanisms most people never recognize. Understanding how our planet's 23-degree tilt drives everything from tornado migrations to polar ice collapse helps you make sense of the dramatic changes happening around you right now. Share this knowledge with others and stay informed about ongoing seasonal pattern changes. The cosmic accident that created our tilted planet isn't finished transforming our world.